Over the next few lectures, we're going to advance to the intermediate student language and learn a new language construct called the local expression. What local expressions let us do is to have definitions, functions, and constants that are only available within one small part of the program. Once we learn how local works, which we'll do over 3 short videos, then we're going to look at 2 important ways to use local. One has to do with organizing programs that are large or written by more than one person. Another has to do with dealing with important In this first video on how local works, I'm going to give you the basic intuitions for local expressions and also show you how to write well-formed local expressions. Well, it's graduation time once again. We're going to move on to a higher level learning language. So as before, I go down to the lower corner here and I click and I get a menu that you can't see right now. I have to click on Choose Language and then I get to choose Intermediate Student under the How to Design Programs languages. So now I'm an intermediate student. And it's yellow because I haven't run yet. As soon as I run, it won't be yellow anymore. So what we're going to do now, the reason we switched to this new language is to get a new language construct called local. And our presentation of local is going to be broken up over several short videos. I'm sure you'll be glad to get a short video after some of last week's videos. So here's an example of using local. I won't type the whole thing out, I'll just put it here for you to see. And in a minute I'll talk about the rules, and I click and I get a menu that you can't see right now. I have to click on Choose Language and then I get to choose Intermediate Student under the How to Design Programs languages. So now I'm an intermediate student. And it's yellow because I haven't run yet. As soon as I run, it won't be yellow anymore. So what we're going to do now, the reason we switched to this new language is to get a new language construct called local. And our presentation of local is going to be broken up over several short videos. I'm sure you'll be glad to get a short video after some of last week's videos. So here's an example of using local. I won't type the whole thing out, I'll just put it here for you to see. And in a minute I'll talk about the rules for forming local. So I'll more precisely talk about the different parts of the local. But intuitively for now, the local has 2 parts. It has the definitions, which are here, and the body, which is here. And the way to think about the local is it says, hey, these definitions, they're valid only inside the local. They're not valid anywhere else. So if I run this program, you shouldn't be too surprised to get the result is 3. Because this says, hey, inside the local, A is 1, B is 2, and this thing called the body is an expression which is evaluated to produce the result of the local. So that's a local where all of the locally defined definitions are constants. Here's a local in which one of the locally defined definitions is a local constant. I'm putting those in lowercase. And the other locally defined definition is a function definition. Local will let you have any definitions you want in this define part. You could even put a define struct, but we're not going to do that. So this says, hey, there's this locally defined constant p, the value is Akio, and hey, there's this locally defined function, and the body of that function happens to refer to p, but that's okay because p is defined as a constant inside this local. So if I say run this, then I get Akio port key. Okay? The way to think about it is it's almost as if I had done this. Only almost as if. It's different in important ways. But it's almost as if I had done this, where the definitions were what's called at top level. They weren't inside a local. And I just did that. But it isn't that. It's quite different, and it's different in an important way, which is these definitions are only valid inside the local. So in particular, if I try to use A out here, it says there is no A, because the A is only defined inside the local. Or if I try to use fetch out here, it's not valid out here, because it's only valid inside that local. So that's the way in which it's different. Now, in the next two videos, I'll talk more precisely about the exact way in which it's different. But let me now just talk more precisely about exactly how you form a local. We're going back now to the kinds of slides we saw way back in the first week of the course. The rule for forming a local is straightforward. Balanced body, which is an expression. You've already seen that local lets you have definitions that are available inside the local. But what does that mean exactly? Are they available outside? What if there's a definition outside the local and inside the local that has the same name? What if there's a local inside a local, or even one more local inside of that? In this video, I'm going to talk about the concept of lexical scoping and show how scope contours will let you answer any such question about local. In this video, I'm going to talk more precisely about what it means to say that local sets up some definitions inside the local expression. To do that, I'm going to introduce an important concept in programming called lexical scoping. Let me set up a little problem here for us to think about. Let me get rid of that local expression, and I'll say define P is incendio. Now, the question is, if I run this program, what am I going to get? Am I going to get accio port key or incendio port key? I'll put a space there. That's not key to the problem. Which of the two am I going to get? Well, I'm going to get accio port key, which is the one I want, of course. But the question is why? And in order to talk about that, I'm going to introduce this concept of lexical scoping and scope contours. So the first thing to understand is that in a program, there's a thing called the top-level scope, the global scope, the scope of the whole program. So the way to think about that is that there's a box kind of around this whole program. And every definition in that box is recorded in the box. So in this global or top-level scope, we have recorded the fact that there's a definition for P. So there's a little notation here that says, hey, there's a P in this box. Then whenever we encounter a local, we make another box just around the local. And every definition that's in the local gets set up in that box. So whereas the top-level scope, the top-level box just has P, this inner scope, this inner box, has P and fetch. Okay, so that's the first half of lexical scoping. The second half is, what do we do whenever we see a reference to a constant or a function? Well, here's what we do. It's easy. We start right at the reference, and we go to the innermost enclosing box. And we see if that innermost enclosing box has a definition for that reference. So starting at this P, we go to the innermost enclosing box, which is the box of that local, and we say, hey, is P defined here? And the answer is yes, it is. And then that's it. We're done. We know which P this is. It's the P that we find in the innermost enclosing box that defines it. So this P here is the one from this box, so it's accio. Okay, here's a little bit more complicated case. I'm just going to paste it in here. Here's a little bit more complicated case. Well, what's this going to produce? Before we run it, let's try to use the scope contours to figure it out. In the global scope, there's going to be two definitions, A and B. And it's these definitions here, where A is 1 and B is 2. And way down inside this local, there's going to be one definition for B. And in this definition, B is 3. So now let's go look at all the references. What are they each going to be? Well, this first A, we start at the reference A, and we go to the nearest enclosing box, which in this case is the global scope, and we say, is there an A there? Yes, there is. There's an A here, and so that A would go to this A here. We'll just draw a little arrow that says that that A is that A. That reference to A goes to this definition of A. Okay, now let's find the next reference in this program. Well, here it is here after the plus. It's this A right here. Well, which A is that? We don't know. Let's go to the nearest enclosing scope contour. It's this inner box. Does it define an A? No, it doesn't. Let's go to the next nearest enclosing box. It's the outer box. Does it define an A? Yes, it does. So this reference to A here goes to the global definition of A there, or the top level definition of A there. Okay, what about this B? Well, we do the same thing. We start at the B, we go to the innermost box, we say, does this box define a B? Yes, it does. So this B goes to the inner definition of B. Let's go to the next reference. Now let's be careful. This B here is outside of the local. So when we go to look at the nearest enclosing box, it's the global scope. So which B does this end up being? it ends up being the global B. So with these arrows on this, we can kind of see that, let's see, this is going to be plus 1, also 1, 3, and 2. 1, 1, 3, and 2 is, I think, 7. Sure enough. Let me suggest that you do some exercises. I'm about to give you some to do with these scope contours, and you can kind of check your work automatically with Dr. Racket, but please, it's the globals it does. So this B goes to the inner definition of B. Let's go to the next reference. Now let's be careful. This B here is outside of the local. So when we go to look at the nearest and closing box, it's the global scope. So which B does this end up being? It ends up being the global B. So with these arrows on this, we can kind of see that, let's see, this is going to be plus 1, also 1, 3, and 2. 1, 1, 3, and 2 is, I think, 7. Sure enough. Let me suggest that you do some exercises. I'm about to give you some to do with these scope contours, and you can kind of check your work automatically with Dr. Racket, but please, 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 let me encourage you to first try to solve these problems on your own before you use this trick I'm about to show you to check your work. In Dr. Racket, in the intermediate student language, when you've got locals, if you click on check syntax and then you hover over a reference, it will draw a line from the corresponding definition. If you hover over a definition, it will draw lines to all the corresponding references. Okay? So that B is that B. Right? So you can check your work this way. It doesn't draw the boxes. It doesn't draw the boxes, but it does draw a line showing you which A it is. So you can use that to check your work, but please, please, please practice some of this scope contour stuff. Let's go to the next nearest enclosing box. It's the out or the top level definition of A there. Okay, what about this B? Well, we do the same thing. We start at the B, we go to the innermost box, we say, does this box define a B? Yes, it does. So this B goes to the inner definition of B. Let's go to the next reference. Now let's be careful. This B here is outside of the local. So when we go to look at the nearest and closing box, it's the global scope. So which B does this end up being? It ends up being the global B. So with these arrows on this, we can kind of see that, let's see, this is going to be plus 1, also 1, 3, and 2. 1, 1, 3, and 2 is, I think, 7. Sure enough. Let me suggest that you do some exercises. I'm about to give you some to do with the scope contour definition. It will draw lines to all the corresponding references. So far, you've seen the basic intuition behind local expressions, and you've seen how the concepts of lexical scoping and scope contours allow us to know exactly which definition provides the value for a constant reference or a function call. But we don't yet have a precise model for how local is evaluated. And without that model, we can't know the exact value of locally defined constants when they appear inside of function definitions. So what I'm going to do in this video is show you the exact evaluation rules for local, and we'll just work through that step by step. And this is going to be really important for the way that we use locals when we get to function abstraction. In this video, I'm going to talk about the actual evaluation rules for local expressions. And I'm going to do that because it'll help you understand some of the ways that we're going to be making use of local in function abstraction a little bit later in the course. So here we go. I've got another example here. This one is slightly simpler than the super complicated one we saw last time, but it's complicated enough to talk about what we need to talk about here. So, intuitively we could see what's going on here. That B and that B are the outer B, and both of those inner B's are the inner B. So that's plus 1 times 2, 2 is 4, so plus 1, 4, and 1, pretty sure that's 6. It is. But let's talk about how ISL actually evaluates the local expression. So the first thing to remember is that local is an expression. It doesn't affect the evaluation of expressions outside of it. All expressions are like that. So let's start by evaluating this whole expression. Open paren plus. Plus is the name of a primitive operation. So this is a call to a primitive operation. We need to reduce the three operands, this B, this local expression, and that B, to values. We start with the first one. Is it a value? No, it's not. It's a reference to a defined constant. We happen to be using lowercase names here, but that's a style guide issue, not a language issue. So B is going to be replaced by 1. So the first evaluation step is just that B gets replaced by 1. Nothing's happened with the local yet. We haven't seen it yet. Okay, now let's do this local. Now, the way local evaluation works is that 3 things are going to happen in one step. Okay? There's going to be a thing called renaming. There's going to be a thing called lifting. And then we're going to replace the entire local expression with its renamed body. Let's first talk about the renaming. The first thing we do is we take every definition in the local, in this case there's just one, define B, and we find all the references to that definition. In this case there's these two. We can either do that ourselves or we can use check syntax to help us. There's those 2 definitions. And now we come up with a new globally unique name for B. What I'll do is I'll make a copy to work in. Just to keep it simple, what I'm going to do is I'm going to rename B to B_0. And at the time I do that, I'm going to rename all the references to B to B_0. Now, if B_0 already existed, I would use something else. The key thing is it has to be a unique name. There can be no other definition in the world that has this name. Okay? Technically, it's actually, there could be no other definition in the top level scope that has this name. And technically, actually, the renaming works in a more subtle way. But this explanation is good enough to understand the evaluation of any program we're going to write. Now that I've done the renaming, I do another thing, which is that I take the renamed definition and I lift it out of the local so that it's now in the top level scope. And notice I don't lift it just out of the local. I didn't put it here. I did not put it there. I have to lift it all the way to top level. I lifted it all the way to top level. If you want, you could go put it all the way up here with the other definitions. You don't have to do that. It really just has to go to top level. So I did the renaming, I did the lifting. Now the third step is I replace the local with the body in which the renaming has happened. And now notice something important. There's no local anymore. The local is gone. That's the same kind of thing we saw with if and cond. If tried to get itself out of the way. It evaluated the question, and then it replaced itself with either the true answer expression or the false answer expression. That's what's happening here. The rules for evaluating local are trying to make the local go away so that it'll have a program in BSL. This is now a BSL program. It's not an ISL program anymore. Local is gone. And so now we just keep evaluating. And of course, since it's a BSL program, it's quite straightforward. Let's see, which B0 is this? Well, it's that B0. So this will become, in the next step, that B0 will become 2. In the step after that, the next B0 will become 2. In the step after that, the times 2, 2 will become 4. In the step after that, this B, well, which B is that? That's this one way up at the top here. That's going to become 1. Whoops, I need to actually do the step. Yeah, that's going to become 1. And in the final step, that whole thing is going to become 6. The key thing about the step-by-step evaluation, or about the evaluation rules for a local expression, is when you get to the local, first you rename each definition and all of the references to a globally unique name. So if there were multiple definitions here, you would do this for all the definitions. So in this case, we renamed B to B0. You rename the references also to B0. Then you lift the definition to top level. There it is. And then you replace the local by its body. So that's the rules for evaluating a local. Rename, lift, replace the local with its body. Be sure to practice that, because understanding how we're going to use local in abstract functions is going to In this video, we're going to look at encapsulation, which is the first important way that we're going to use local. Encapsulation is one of the most fundamental concepts in software engineering, and this is what it's about. Imagine a large software system with 10, 20, 50, or 100 programmers on it. Now ask yourself, how likely is it in that situation that 2 programmers are going to want to use the same function name for 2 completely different functions? It's pretty likely, right? It's almost guaranteed to happen, in fact. And that's the problem that encapsulation solves. What encapsulation lets us do is to take each part of our program and make it into a capsule, a little package that has a bunch of internal functions and constants and structures, and only a small number of external functions and constants and structures. What encapsulation rests on, and I'll explain why we call it encapsulation as we go, but what encapsulation rests on is the observation that with a local, The A and the B in this example don't exist out here. If we draw the scope contour, that A and B don't exist out here. Now, why would that be useful? Well, let's go to FSV4, which is the file system example we did last time. Now, when we designed the functions in this file, because we had mutually referential types, we always ended up with two functions with these kind of silly names. There was some data element and some data LOE. And really, from the perspective of someone who's holding on to an element and wants to sum all the data, they don't care that there's two functions. They really only want one function, and they would like it not to have this silly name. But the function they want to call some data has to have this helper. So how can we fix that with local? Well, watch this. I'm going to do it once quickly, and then I'll come back and do it slowly. What I'm going to do is I'm going to say, really, the function that the rest of the world wants to call is a single function that operates on an element. So I'm going to give the rest of the world a single function that operates on an element. And I'm going to put the two functions I wrote before as locally defined functions. I'll press Command I to fix my indentation. So now the two functions I originally defined are in there. I gotta go change the name of all these tests. Let's try it. Unit tests for silly names, the more the better. So there we go. That's a first example of encapsulation. Now what I'm going to do again is to do the process of converting multiple functions into a single function with encapsulation more slowly. I'll work through the process more slowly, telling you what each step is, and then I'll leave you to do the third example on your own. So let's go down here to this next one. The first thing is to identify some functions that are a good candidate for encapsulation. And what makes these functions a good candidate for encapsulation is that there's two or more functions that work together. Another way of saying it is that there's one function that has one or more helper functions, and the rest of the program really only wants to call one function. In this case, all names operating on an element is really the only function that the rest of the program wants to call. All names dash LOE is just a helper for all names dash element. So the first thing is to identify a candidate that has this property, that there's a function with one or more helpers, and the rest of the world really only wants to call one function. The next thing to do is to think of a name for the function that the whole world will call. Sometimes one of the functions already has that name, sometimes it doesn't. In this case, I think all names dash dash element is a lousy name for the rest of the world to use, so I'm going to make up a new name. So I put the function header like that. Then I say local and an opening square bracket, and I go after the last of the functions and I close the square bracket. I'm not going to fix the indentation yet. I will in just a second. And then I write a trampoline that calls the appropriate one of the multiple functions to get things started. I close all the parentheses. I type Command I to fix the indentation. So now I've done the encapsulation. I just have to clean up the paperwork. First thing I have to do is, if there were multiple signatures, now there's really only one. Now there's just the signature of the function that the whole world sees. So I'll get rid of the second signature. and I'm going to clean up the tests. Oftentimes this is going to mean getting rid of the base level test, and I'll talk about the implications of that in a minute. I'm going to first get rid of the tests for the function that we don't have anymore. Then I will do a renaming of all the other tests. I'm going to copy that. I'll say find, come down here, find that, replace it with that. I'll say replace, 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 replace. These stubs, you know, there's two choices now. I could do that replace and get rid of the second stub, get rid of that S. That might be one thing to do. Or you could just delete the stubs entirely. And now, of course, whenever you do something like this, you test right away to make sure you didn't mess up. And I didn't mess up. Now, the way I did that process so methodically follows this notion of a refactoring. The idea of a refactoring is you're going to make a change to a program that doesn't change its behavior at all. It just changes its structure. Sometimes you want to do a refactoring and then change the behavior. You should avoid the temptation to do both of those at the same time. First do the refactoring, check it in front of you all along, and you should have been doing this all along, but I'd like you to go ahead and do this one. I did the whole thing, and there we go. So far in this course, we've avoided talking about performance or program efficiency. And we've done that quite deliberately. The reason is that it's very easy for programmers to worry too much about efficiency, too soon about efficiency, or to be honest, to worry just plain incorrectly about efficiency. As a general rule, it's a better idea to design a simple program that's easy to understand and easy to change, and then worry about the efficiency later, once the program is running. What you can do then is you can run the program against a sample data set and measure its performance and see where the real performance problems are. What you'll find is you often get surprised. Some of the things you thought would be a performance problem get taken care of automatically by the programming language implementation. Other things you might have thought would be a performance problem turn out not to be. And then unfortunately there's some other things that you didn't think would be performance problems that turn out to be performance problems. That said, there's one category of performance problem you really need to fix as part of the design. That has to do with problems of exponential growth in the time it takes your program to run as the data gets larger. Right? Exponential growth in performance is not going to be a good property for your program to have. So what we're going to do in this video
This week's design quiz had 2 problems for you to complete. The first asks you to design a function that consumes 2 rosters of players and produces true if all players on both teams will get to play. The second problem assumes that 2 teams have the same number of players and asks you to design a function